Right. So this time around, we want to look at application of derivatives. Now, derivatives or differentiation has a number of applications. Among them, we can use derivatives to look at rates of change. And here, when you're describing rates of change, we're basically looking at how fast a certain parameter is changing, a certain quantity is changing with respect to, sometimes it will be with respect to time, sometimes it will be maybe with respect to another variable to say how fast is it changing when this changes. So those are rates of change. So another thing that we can describe here, or that where we can use the derivatives, is going to be in determining, coming up with equations for turning points, or finding turning points themselves. Because what you should understand is that at a turning point, the gradient is going to be zero. So we're going to see exactly how a derivative will be used to determine the gradient of a line. So when you differentiate a function, what you actually get is an equation that gives you the gradient at any point on that function. So we're going to use derivatives to determine turning points. Okay, so that is going to be one use. But there'll be a number and a number of concepts. And under turning points here, we're going to have the concept of maxima, minima, and then from there, we're going to look at the use of the same derivatives to analyze or find equations of tangents and normal lines to a function. So if you're given an equation of a function, how do you get the equation of a tangent to that curve? And also, how do you get the equation of the normal to that curve, maybe at a specified point? So the last part of this, we're going to look at things to do with Rolle's theorem. So we're going to look at this. And then Rolle's theorem is going to move hand in hand with the mean value theorem. So those are going to be right at the far end when describing these concepts. So these are going to relate to, or they're going to lead us towards the final concept, which is going to be the L'Hopital. Okay, so we're going to look at this as well. So this is a concept that you have seen already, but now we're just going to look at it from just for specific conditions or cases. And this is going to be the last part of our description under applications of derivatives. So some of these are going to look at them in one session. Some of them we're going to take maybe one or two sessions to look at them, but most of them we're going to look at one session, sometimes even just do two in that one session. Now, let's look at the first one, rates of change. So under rates of change, what is happening? So this is where I was describing to say that here, you want to understand how a certain parameter is changing when something else changes, or when a variable changes, how does something else change? So an easiest concept that I can give you to understand the rates of change is perhaps how distance changes with time. That is a simple example of a rate of change. So I can say that, okay, you have a certain object whose path is described by, I can even say a parabola, something like this. So this object is running around a parabola like that. And then you know to say the equation, since this is the path the object is following, this is the path, and the path obeys, or it can be described in form of a parabola. Maybe y is equals to negative, basically just some function f of x. So that is the path. This is a parabola defined by that. Well, in this case, we can actually determine how fast the distance is changing with respect to time. And to do that, we would need to get the change in the distance with respect to time. This will give us the rate of change of the position of this object with respect to time. So basically, a rate of change is just going to be a derivative of a parameter with respect to time. This is what rates of change are going to be. They tell us the dependency of one variable on another. Okay, so I think we have a few questions that we can use to just understand this. Consider an example where we have the expression that relates the light or the luminous intensity to the voltage V. So here we're saying that I here is representing the luminous intensity in candelas. So, and it's relating to the voltage in that supply or in that line by this expression. So if this is what you have, what are we supposed to do? The question is now saying determine the voltage at which the light is increasing at a rate of 0.6 candelas per voltage or per watt. Sorry, not per voltage, per watt. So we want to find what the voltage will be when the rate of change of the intensity is equivalent to 0.6 candelas per watt. So what is happening there? Well, look at what this rate is. According to what the rate is, they're saying the rate here is equals to 0.6, and they're giving a unit. And for the unit, they're giving us the candelas there, and they're saying per watt. So what is this telling us? It's like on top, you've got luminous intensity. Down, it's something to do with the voltage. So what happened for us to end up in that situation? So to get the rate of change they are describing, we are differentiating. And what are we differentiating? Based on what we are seeing here, we have light intensity or luminous intensity over voltage. So they analyzed how the luminous intensity was changing with respect to the voltage. This is the rate that was evaluated. So when you get this derivative, when you differentiate, we are differentiating with respect to V. So if you perform that derivative, the 2 comes down to multiply the 4 by 10 to the power negative 4. And then we know to say the power there reduces by 1. So this will just be V now. So don't mistake the V here for to be a unit to say that's the volt, but instead that V symbolizes the voltage in this case. So this becomes our derivative. But we want to find what V is. We're finding this term here. Want to find V there. So we're saying, what is V when the rate, and what gives us the rate? The rate is given by di over dV, the change in the luminous intensity with respect to voltage. Want to find what V is when this rate is actually equals to 0.6, meaning that our expression reduces to 0.6 is equal to the right-hand side will be this, which is 2 by 4, which is 2 just 8 by 10 to the negative 4 times V. So in the end, divide both sides by 8 by 10 to the minus 4. And then this side as well, 8 by 10 to the minus 4. This goes away, so that now the voltage will be equals to 0.6 over 8 by 10 to the minus 4 volts. So this is how you determine the voltage at such a point. Consider the third question here. And what are they asking us to do here? Here we have a ladder that is 12 meters long, and this ladder leans against the wall. The foot of the ladder is pulled away from the wall at the rate of half meters per minute. At what rate is the top of the ladder falling when the foot of the ladder is 4 meters away from the wall? Now, this is a little bit complex, but it just requires you to understand exactly what is happening. And the first thing that you want to do is to create a mental picture of your problem. So just create a simple sketch as they present. You have a 12-meter long ladder, and this leans against the wall. So what is happening? So it's like you have a wall here. You can write it however you want. I'll write my wall to be somewhere here. But let me favor the other orientation for no reason really. Okay, so you go like this. This is our wall, and our ladder, let's say this is, I can even say it like this. This is our ladder like that. Then this is the ground. Okay, so you have something like this. Now, what is happening here? So we have our ladder in place. It is 12 meters long. So the length, since the ladder is 12 meters long, it tells us that from here up to here, it is actually 12 meters. So I'll just keep my L is equals to 12 meters. So it leans against the wall, which is what we're demonstrating there. The foot of the ladder is pulled away. So the foot of the ladder, somewhere here, this is being pulled away. What are they saying? The foot of the ladder is being pulled away, is being pulled from the wall at a rate of half meters per minute. So this is being pulled in this direction, and the rate is half a meter or half meters per second, per minute, I mean. At what rate is the top of the ladder falling? So the top of the ladder is this. At what rate is it falling downwards? Okay, now what you need here is an equation. So this is going to be a pattern every time when you're dealing with questions to do with this. It will be the same thing for question 4. You're going to follow the exact same structure. I think even for question 8, question 9, we're going to follow something similar, but use, is it maxima here or what? Total area, dimensions, maximize. I think these are going to be different. Determine the dimensions to minimize. Okay, but I think it's going to be something related. But what you want first is an equation that connects everything. You see, since you're dragging this away, what it means is that this dimension, the base of the ladder, it will be increasing. And what they're looking at, how fast the ladder is falling, notice that how fast the ladder is falling has to do with this dimension, the height in that side. So basically, to consider or to determine how fast the top of the ladder is falling, you have to determine how fast the height is reducing. And that rate where they're saying we are pulling the base away at that rate, we'll have to just measure how fast the base is increasing. That is what that rate is. So in other words, we want to find a connection between the height, the base, and to say we can connect this with the length of the ladder there. And since when you consider the shape we are forming when we do this, this is a right-angled triangle, and all the sides of a right-angled triangle will be connected by Pythagoras theorem. So let's do at least that part. We'll get this. And let's bring this down here. So by Pythagoras theorem, the longest side, which is L squared, will be equal to the height squared plus the base squared. So this is our starting point. Okay, what else here do we have here? Okay, so we can actually get we can get the derivatives here. But do we want to get the derivative? What rate have we been given? So look at this. The rate that we've been given, it has been given in terms of what? We have a rate, and this is half, which is 0.5, and this is meters per minute. So in other words, our rate here is being measured with respect to time. We're seeing how a length is changing with respect to time. Based on that, when we get our derivatives must be obtained with respect to time. Now, what we will do here, once we have the relationship between our dimensions, we're going to get the derivative. We know in the end, we're going to get the rate of change, how fast something is being pulled. But before we get there, we're going to differentiate here, but we're going to differentiate this implicitly. I hope you guys remember how we conducted implicit differentiation. And the worst part here is all these functions are changing with respect to time. Perhaps except maybe basically they're all changing. But look at what is happening here. You have this, the height is reducing, this is increasing, perhaps this part, I think that part is going to remain constant if we're looking at this with respect to time. Yeah, the height there is going to be, the length of the ladder, I mean, is going to remain constant throughout. So with respect to time, the length of the ladder L will not be changing throughout. The length of the ladder will be constant. So regardless of how fast this is being pulled, the distance from here to here will still remain the same, being the length of the ladder. So what are we doing? We know h is a function of time. H depends on what time is. After a short period of time, maybe when the ladder is here, when the base of the ladder is here, we see that this is going to be something like this. The height is longer, it's a bit higher. But after a bit longer in terms of time, we see that now this has been dragged a bit more. The height would have reduced. And the more we pull, the longer we pull, the height keeps reducing. And as the height reduces, the base keeps increasing. So one is reducing, one is increasing. This is basically what is happening. But throughout, the length of the ladder L remains constant. So H depends on time. The base depends on time as well. But L does not depend on time. L is a constant. So in differentiating this expression implicitly, you have to remember or observe that this L here is a constant. It's the same as 5 squared. In fact, it was even given that this is a 12. So we might as well even just write that the length there is 12 squared. H is that. B is that. So you have 144. Now, there'll be problems where every quantity will be changing with respect to time, but this is just not one of those. Here, L, I mean, is constant regardless of how long we drag that. Okay, so this is where we are. You can choose to make one of these quantities subject of the formula, but here it is easier to just choose to differentiate this expression implicitly. And we're doing it with respect to time. When you differentiate the first part, that's just a number, you get 0. When you differentiate h, remember how you differentiate something implicitly. First, differentiate it the way it is, you get 2h. The power there reduces by 1, it just becomes a 1 like that. Now you have to multiply it by dh, dt. So this is how you differentiate implicitly. Yes, please?
Are we going to include the value of b? No, we've been given it in the question.
What value of b? Or that value to say at that point? This one here, the ladder is 4 meters away from the wall.
Yes.
Okay, this one will come, but at a later point. You have to understand that I included the 12 for one simple reason. Regardless of how much we pull, the length of the ladder does not change. If I just give you that description again, when the base, let's start with when the ladder is way up, something like this. Notice that in this case, the height comes up to there. So the height is all the way from here up to the top. This is your edge. But what is your base? Your base is from here to here. But it's the same ladder. It doesn't become shorter. It doesn't become longer. But what happens? Since we are dragging only the bottom, while the top, it's like it's basically just sliding down on our wall. By the time the ladder is in this position, look at what has happened. The height is now only up to here. The height has changed. Look at the base. The base has become a little bit more. But has the fact that the length of the ladder, okay, has the length changed here? When it was like this, the length was 12 meters. But after dragging the base more, has the length changed? It hasn't. The length is still 12. Even after pulling for some time, a bit longer, something like this now. What has happened? Now the height is only up to here. The height has reduced further. What has happened to the base? The base has increased again. So we see that the base keeps increasing, the height keeps reducing, but the length L of the ladder remains 12 meters. Do you agree now?
Yes, sir.
Okay. So because of that, we put that 4 where we have the base, because it was not always 4. When we started, we can argue that it was less than 4. And as time continues or proceeds, it exceeds 4. But we want to analyze when it is 4. But before we get to when it is 4, we are describing generally how are these quantities changing. So this is why we say, okay, H is changing. We have differentiated H. In the same way, we differentiate B. Also depends on time. So we will have 2B, and then we'll multiply by dB dt. So we're saying that, okay, dH, H is changing with respect to T. dB dt, B is also changing with respect to T. So this is the expression that we now have. So from here, we can move things around. We end up with 2 H dt is equal to 2B negative dB dt. The 2 and the 2 can cancel out. We now have H dH dt equal to negative B dB dt. We are now here. You see, what this gives us, it's the connection of how the two quantities are changing, how these two rates are connected. Here it even shows you the fact that one term is negative or the other is positive. It shows you to say one is increasing, the other term is reducing. But more importantly, when you check the question, in the question, what are they saying? They're saying that we want to find, where is that? At what rate is the top of the ladder falling? So I want to find how fast the height is changing, or how fast it is reducing. But what else? When the foot of the ladder is 4 meters from the wall. So the foot of the ladder is 4 meters from the foot of the wall. Have they said anything else? So the foot of the ladder is being pulled away at the rate of 0.5 meters per minute. So you might describe that one to say the foot of the ladder controls the base. So it tells us dB dt. So the foot of the ladder is being pulled at 0.5 meters per minute. This is how fast we're pulling it. Now we want to find the dt, a specific point, at which point when the base, when this is 4 meters from the wall, meaning the base is 4 meters. This is what we want to do. So what do we end up with? So from here, we end up with dh dt, which is what we are looking for. This will be equal to negative b over h dB dt. Now we have to start substituting. This is when we actually plug in that 4 meters, the base, because we now want to zero it down to a specific point. But we still have to also know what this h is, because I think from when I was writing those, everything else is clear. dB dt is this. B is 4. But how about h? To get h, here's what you would do. The ladder has been falling for some time. It has been falling such that the base is now 4. The base is now 4. But remember, the length of the ladder was never changing. It was always 12. So notice that now we can use Pythagoras theorem again, so that now it gives us h. So we have 12 squared is equals to h squared plus 4 squared. So this tells us to say that, oh, okay, at this point when the base was 4, what was the height? So it tells us the exact height when the base was 4. So we're going to have height squared is equals to 12 squared minus 4 squared. And this will be equals to 144 minus 16. So this would be the square root of 144 minus 16. What is this giving us? So we get 11.3 meters. So now we can plug in here. So we have negative, our B is 4, our height is that 11.3, our rate of change of B with respect to time, this is that one which was 0.2, and this was in meters per minute. So this is in meters, this is also in meters, this and this will cancel, so that now you just have to multiply 4 by 0.2 divided by 11.3, then times the meter per minute. I don't even have to put this multiplication. So what?
Sorry, it's supposed to be 0.5 meters.
Oh, sorry, yeah, this is 0.5, yes, 0.5. Okay, so this ends up giving us minus 2 over 11.3 meters per minute. Okay, so what will be the answer here?
Negative 0.177.
Okay, so this is our dH dt. And this is what they actually wanted. Now we have a negative. What does the negative mean? The negative actually is just telling us that this height we're looking at this height is reducing. This is how fast the height is reducing. The question was not asking us how fast the height is reducing. It was asking us how fast the top is falling. But the way the top falls has to do with exactly how the height is reducing. So the two are proportional, or they are relative. They are basically one and the same. So you might as well conclude that, therefore, the top falls at, now I'll skip the minus because it's being specified on the fact that this is falling at 0.177 meters per minute. So I can present it in this way, but if I want, I can still convert the minute to the seconds. So I can still convert this to meters per seconds instead.